These are the examples for Geometry B, Credit 2, Lesson 12.4. Lesson 12.4, again, we're doing some more work with similar triangles and also finding a missing side length. And we're going to end up with some application, which means we'll be doing some word problems and seeing how this we could use this in a real-life situation. All right, so let's take a look here. We're at the directions for 1 and 2. It says the triangles are similar. What is the area of the larger triangle? So on this one, we are going to solve for x, but we're going to go a step further. And then once we know what x is, we're going to use the area formula to calculate the area of the larger triangle. But one thing at a time, let's first of all solve for x. So our corresponding sides would be 40 and x. So we're just going to work left to right. We're going to go 40 over x. Now, as we saw in the last video, you could do x over 40 as long as you do 75 over 60. But so as not to complicate things, we'll just do 40 over x. And then again, if we're going left to right, we'll do 60 over 75. So notice in both cases, the 40 and the 60 are in the numerator. The x and the 75 are in the denominator. All right, so now we're going to cross multiply to solve. We have x times 60 is 60x. Going the other way, we have 40 times 75. Bringing down that 60x, and we're going to simplify that 40 times 75, which gives us 3,000 exactly. Our final step, x is being multiplied by 60, so we divide 60 to both sides. The 60s cancel out, and we have 3,000 divided by 60, which gives us 50. And so we know that x is 50. So that's the first thing we have to do is we have to solve for x, and we've done that. We know that x is 50. Now, they want us to find the area of this larger triangle. So remember the formula for area of a triangle is the base or the bottom times the height divided by 2. And so the base here is 75. The height, and when we say height, we mean that straight up and down perpendicular to the base distance, which is 50, which is what we just found over here. And of course, we're going to divide by 2. The dividing by 2 is just part of the formula there. So the first step is to simplify the numerator. We take 75 times 50. That's 3,750. And we divide that by 2. And we get 1,875. 1,875. And these measurements, we didn't put them up here, but let's go ahead and do that now, are in feet. So whenever we're finding area, we want to put the appropriate measurement. So it's feet, but area is always in square units. So that would be square feet. So 1,875 square feet. By the way, before we go on to the next example, you might wonder why it's in square units. You might not wonder, but hopefully you do. So let's take a look here. Let's look, before we go into example for number 3, if we had a rectangle with a length of 3, so this is 3, and this is 2. Now a rectangle, it's the formula for area is just length times width. So 3 times 2 is 6, and this would be 6 square units. And you can see why. Because we have, or hopefully you can see why, I'm pretty sure you can. We have 1, 2, 3, 4, 5, 6 square units. Now, it's not a coincidence. We could have done a much bigger triangle, but that'd take a lot more time. But I think this illustrates the idea. We have 3 this way times 2, and we get 6 squares. That's why we say square units. So 1, 2, 3, 4, 5, 6 square units. Now, we said units. We could have made, we could have made it meters, in which case that would be 6 square meters. So just a little insight there as to why area is in square units. All right, problems 3 and 4, it's kind of the same thing, but once again, we have one of these situations where the triangles are oriented slightly different, so we're going to do an example for each one of those. So what we're doing on problems 3 and 4 is if you have a triangle, in fact, let's get rid of this for the moment. If you have a triangle and then you draw a perpendicular segment from one side to the vertex of the other, what you've now created and it's a good thing, is three similar triangles. This triangle here, this triangle here, and then the entire big triangle are all similar to each other. And what you have to kind of view is imagine, of course, this is a right triangle as well, is imagine turning this triangle this direction so it would land kind of not on top, well, on top of, but and you would see how it's similar to this little triangle here. And of course, the big triangle is similar to both of them. Let's call this one the medium and this one the small one. So if we're trying to find the length of this perpendicular here, we're going to find something or calculate something called the geometric mean. Now you might remember the word mean, or maybe a teacher said to you, I know I've said it, mean means average. You say, oh, I get it. We, add them up. There's two numbers, so we divide by 2. Not so fast. That's the arithmetic mean. We're doing the geometric mean. So how do we do geometric mean? Well, it's almost as easy, really. All we do is we take these two segments, the 100 and the 81, and we're going to multiply them together. So 100 times 81 gives us 8,100. Whoops. And then we're going to take the square root of that result. So it's the square root of the product. Remember, product is just a fancy way of saying multiplying. It's the square root of the product multiplying these two numbers here. So 100 times 81 is 8,100. And let's remind you on Desmos how you can actually, if you turn your phone, most phones, if you turn it sideways, you'll see the little square root symbol. But let's go ahead and show you on Desmos here. And let's go ahead and share our screen here. And here we go in just a second. There we go. All right, so Desmos, you can see that, should be able to see that on the screen now. So remember to get the square root symbol, you bring up the keyboard, and then right there, third on the bottom row, third column over, there's the square root symbol, and then just type in the 8,100, and the answer is 90. And so the length of x here is, I guess we should have put x equals, right? So x equals 90. And that's it. That's all you got to do. All right, so problem number 4, again, same thing. And let's go ahead and stop sharing. And let's go ahead and take a look at number 4. So once again, we're doing the geometric mean. We have this altitude here that's drawn once again from this side to the vertex to where the angle is here of this angle here. So once again, it's the geometric mean. So x equals the square root of 144 times, oops, actually we're doing that's the wrong numbers. Supposed to be the example for number 4, right? Not number 4. We've got a little bit bigger numbers here, actually, 400 and 256. So it's the square root of 400 times 256. All right, so let's go ahead and multiply that together. Thank God for calculators, right? Because these are some big numbers, although not too big of a deal. It takes a little time to do this by hand, but not really that hard. So 400 times 256 is 102,400. And so now let's go back to Desmos. Let's go ahead and share our screen. And once again, let's just remind you how we do that. Bring up the keyboard and square root symbol. Remind you how we get the square root symbol, I should say. And this time we're taking the square root of 102,400. And we do that, and we find out that that's 320. And so x equals 320. So same idea on both problems 3 and 4, just triangles are turned a little bit different, although that shouldn't be a problem, but sometimes we like to do another example just to clear up any potential confusion. So that's the geometric mean for problems 3 and 4. All right, again, pause, rewind the videos as needed. We're not done yet, though. We've got an example for problems 5 and 6. And 5 and 6 are very much the same, the way you do them. So we'll just do one example for both problems 5 and 6. Let's go ahead And I think we're still sharing. We don't want to do that. There we go. All right. So let's go ahead and take a look at numbers 5 and 6. So turning the page to page 46, I'll just read one of these as an example. It says Ryan is, I think in the packet it says 5 feet tall, but our example, we're going to use 6 feet. At a certain time of day, he cast a shadow that is 12 feet long. Actually, let's do it like this. We'll do 4 feet. Let's do it like that. So Ryan is 4 feet tall. We'll do it like that. At a certain time of day, he cast a shadow that is 24 feet long. And this is not the numbers from the packet, but our example. At the same time, a tree cast a shadow that is 60 feet long. What is the height of the tree? So this is what we were talking about in the intro. And then this, by the way, this is our examples for 5 and 6. This is what we're talking about in the intro, where we're going to get into some application here. So here's Ryan here, represented by the stick figure. And he is 4 feet tall. He is casting a shadow that is 24 feet long. And then it says at that very moment, and the reason it says the very moment, because, the shadows, as time goes on, the shadows can change length. And so we have a tree that is casting a shadow of 252 feet. It's a long shadow, which probably means a tall tree. And what they want us to do is to find, it says, what is the height of the tree? So we're trying to find this here. Now, the reason why this works is because we can make a right triangle. We can make a triangle out of these here, even though we don't really need to. And so we can see that we have these right triangles, and we can create our proportion with the information that we're given. So let's go ahead and do that. So again, height of Ryan to height of tree, so 4 over x. And so if we're going from small to big or left to right, we have to do the same thing with these other numbers. So again, left on top, the small one on top, and then 252 on the right. So again, just very important. We want to emphasize that. So we're going little to big. You say, well, how do we know to go little to big? So you don't have to. Remember, we said before, the key is consistency. So we could have went x over 4, but then we also would have had to do, which is fine, 252 over 24. In other words, if you reverse one, you have to reverse the other as well. All right, so as it is, though, we have 4 over x equals 24 over 252. All right, so let's go ahead and solve that. We're going to cross multiply to solve here. X times 24 is 24x. Make that look a little bit nicer so that we can see that better. Oh, forgot the x. Let's try that again. Here we go. Take 2. X times 24 is 24x. And then going the other way, we have 4 times 252. So 24x. And then 4 times 252, we multiply that or simplify that. Either way, we get 1008. And then our final step, x is being multiplied by 24. So we divide both sides by 24. Of course, the 24's cancel there. And we get x equals 1008 divided by 24. And that's 42 feet. So the height of our tree is 42 feet. And if you think about it, that's really kind of interesting, kind of neat, that we can determine the height of a pretty tall tree, a 42-foot tree, by never leaving the ground. Think about that. What we knew here was the height of Ryan, 4 feet. Then we measured his shadow, 24 feet. And then we're trying to find the height of the tree, so that was our x. And then we measured on the ground the length of the shadow, 252 feet. Using that information, we were able to determine the height of this very tall tree. And we can do the same thing with a building, even a mountain. So it's very interesting how we can use these mathematical calculations to really assist us, because otherwise we'd have to maybe climb that tree, and that, maybe would be tough or even dangerous. And so it's fortunate that we have these methods to solve here, to help us solve our problems. All right, so that is it for Lesson 12.4. Again, as we always say, pause, rewind the videos, make sure that you have a good understanding of the work as you attempt the problems. And of course, ask questions. And that's it for 12.4. So until the next video, take care and God bless.